Hello, everybody. So I have here the last problem that we talked about in class, the mechanical energy balance problem with the brine solution. I've gone ahead and already drawn it out and did the necessary information. So right here is the volume flow rate that we have. One thing to note right off the bat is the pump is delivering this flow rate throughout it. So the velocity flow rate here, V dot is going to be equal to the velocity flow rate here and the velocity flow rate here. It's building on the continuity equation. So the volume flow rate is equal to this. We have a density that's given. We have a large cross-sectional area, so that's going to again allow us to assume that the velocity here in this region is slow enough to be considered negligible. The suction line has an inner diameter of this, which I have right here. And then we have another outlet diameter. It goes into an overhead tank that's 75 feet above the liquid level, which I have written here. And then we have that it is frictional losses are equal to 18. It's also giving you that the efficiency of the pump is 70%. So here we go. Here's the diagram that I've drawn out. Let me just do a little bit of labeling here. There's a couple of points that we're going to need to focus on. First one is this point right here. We'll focus on this one and call it point 1. We'll call right here point 2. Right before the pump, and then right after the pump, point 3. And then where the fluid is exiting, we're going to call that point 4. So let's continue forward with this. You're going to want to look at different portions independently depending on what you're looking for. So the first one was asking for the pressure of the pump, but what we're actually going to do is we're going to start with the work of the pump. And to do that, we need to start off with the mechanical energy balance equation. Before I do that, I do want to mention traditionally, you know how the mechanical energy balance is 1 over 2 alpha, and then V2 squared average velocity minus V1 average velocity squared. It's any points that you want to look at. So what I want to do is I want to look at what's happening at point 1 and what's happening at point 4. So we're going to skip everything that's in between and just look at those points. So what I'm going to do is I'm then going to just, instead of writing it velocity 2, I'm going to write it as velocity at point 4. Okay, a couple of things that we get to do here. So again, we were saying that at point 1, it's a large cross-sectional area, so this is going to 0, so we won't have to worry about that. Another thing is defining our origin. We're going to say for this problem, we're going to define this as our origin right here. So that's going to be y equals 0, which means this z goes away right here, the z1. So let's just clean this up a little bit, and I'm going to clean it up with work on the left-hand side since that's what we're looking for. So we're going to have then as this equation, we're going to get negatives popping out in front of all of them. And I just changed this summation of forces into just the frictional force. There's only one force loss. Now here's, we stopped kind of right here when we were going through it. So let's go forward with this term right here. The pressure at point 4. You notice that it's open to the atmosphere. So that's going to be just PATM. Also at point 1 over here, it's also open to the atmosphere. So that's also going to be PATM. So these cancel. So this term goes away, and we get that the work delivered by the pump is equal to this final term here. Okay, so we do not have this volumetric, this velocity flow, but we can find it because we're given the inside diameter of the pipe, and we know that if we're looking at the labeling here, the volumetric flow rate at point 2 must be equal to volumetric flow rate at point 3 equal to the one at point 4 because there's no buildup, there's no accumulation. So we can say that these are all equal to the same volumetric flow rate, or we'll just write just V dot. So we know that V dot is just equal to the velocity at 4 times the area of point 4. So rearranging the velocity at 4 that we're trying to plug in, we're going to take this now plug it into here. Plugging that into here, we get the work delivered by the pump. It's just this. Okay, so we're here so far, and I want to introduce something that the book does. We're using English units here, and it's going to be much easier to just use a shortcut that the book does. And what it's going to do is it's going to divide these terms by G, by a gravitational conversion constant. So what that's going to do is by dividing these terms by essentially 32.2, it allows us to just use the frictional term by itself. Alternatively, you should get the right answer if you decide to multiply this frictional term by the gravitational constant. If you want to dive deeper into why we do that, you can read section, I think chapter 4, section 2, or something like that in the book. But this is just going to cut down a lot of time. So you can convert everything back to SI units if you want. It's going to be a little bit longer to do, but I'm not going to do that here. Another thing to note is this alpha term. This alpha term that was originally defined in the mechanical energy balance equation, that is going to change whether or not it's turbulent or laminar. So for turbulent flow, alpha is equal to 1, and then for laminar flow, alpha is equal to 0.5. So we have turbulent flow that was stated in the problem, so alpha is going to go to 1, so I'm not going to write it anymore. So what we have is we have 1 over 2, I'm going to bring this G back under, GC times volume flow rate, area squared, minus these G's are actually the same value, so you can just get rid of them, and it's going to be just Z4 minus this frictional flow, this work of friction. Now I forgot my negative here. So plugging in, you get 1 over 2 times 32.2. Velocity flow rate, or I'm sorry, volume flow rate, it's right here. And that's in feet, so you can just leave it as 0.2. That means our area has to be in feet, so that's going to be pi over 4 times, it's the area of this section at 0.4, so it's going to be this value. If you just convert from 2.067, you get this 0.17225. It's going to be squared. Then you get minus 74, and then you get minus 18. And you plug that in, you should get something that's, what did I end up getting? Should be something around negative 94, I think. The units of that is going to be feet, pound over, I think it's pound mass. Pound force over pound mass. It's a weird unit, I know, but that's take about doing these problems unless you want to convert everything to SI. So we have that, but I want to now backtrack a little bit because it was talking about the efficiency. So right here, the efficiency of the pump. So this WS that we have in here is the work that's actually delivered to the fluid. So the work that's actually going to be provided from the pump is different than that. So the work divided to the fluid, the shaft work, is equal to the efficiency term times the work that's actually provided to the pump. And this makes sense. So the pump isn't going to be able to provide 100%. If it was, then this would be 100, and all the work that's brought in by the pump is going straight into the fluid here. But it's not, so we have to take away a little bit of it, and that makes sense that the work that we need total is going to be greater than this theoretical work. So work shaft over efficiency, so it's just going to be this value, negative 94 over 70%. That ends up giving you 134-ish. And that's going to be feet pound force over pound mass. So that is the work that's needed by the pump, but it asks for horsepower, so you need to do unit conversions. Okay, in order to do this, Well, actually, let me backtrack a little bit. So this equation is on a per unit mass. So you see how this is pound mass. So even if you're doing SI units, this equation right here is a per unit mass. So per kilogram or per pound mass. And so if you want to get an actual work term, if you want to get into either joules per second or into, in this case, it would be horsepower, you need to multiply by the mass flow rate. So if you take this term right here and you multiply it times the mass flow rate to every term, you get an energy per second term. So you end up getting a joule per second or the English equivalent. So we need to do that first. We have this amount that's delivered, but in order to get the actual energy per second term, we need to say 134 times the mass flow rate, which is just equal to the volumetric flow rate times density. And this was just a simple Google. I just went from grams per centimeter cubic to pound per feet, and it gave you this answer. So we're going to do that. So it's 71.8. So when you multiply these out, you end up getting a value of 1924.24. And the units of these is going to be feet pound force per second. So that's actually an energy term, or a energy per second. And to convert that, you need to go to horsepower. So it is 1,924.24 over a second, and you just divide that by 550, because it's 1 horsepower for every 550 feet, and this is just something that you can Google. So dividing that by 550 should get around something around 3.5 horsepower. Okay, so you should get something around that. Now that was problem number 1. So that was this, finding the work on the pump. We said that it was 3.5 horsepower. Now for the other part. So I went ahead and deleted a couple of things, but I left this mechanical energy balance equation here. Now I said previously that you can do any 2 points you want, and the last part of the question was asking for the pressure around the pump. So we want the pressure around the pump that's being generated right here. So it would only make sense that we would want to do a mechanical energy balance involving 3 and 2, right before the pump and right after the pump. Now, let's plug in the subscripts for that. So V3 minus V2, Z3 minus Z2, pressure 3 minus pressure 2, frictional forces along it, and the shaft work. Something I want to note about this right here, we just solved for that, and this is not going to be WP. It's not going to be what we just solved here. It's actually going to be this value, the value that we took right before we ended up using the efficiency value of 70%, because we want what's actually being delivered to the water. Okay, so let's look at this term here. We have a V3 term, that's going to stay, and V2 is also going to stay. Now we know that the diameter of the pipes are different. V1 is different than D1 is different than D2. So unfortunately, we can't cross these out. They're going to end up being different values, so they have to stay. If the diameters were the same, we can cancel them out. They would just go to 0, but they're not. So let's go to the next term, Z3 minus Z2. Again, we'll say that this right here is our y equals 0. So these are on the same plane, so this term goes away. We want this right here. We want this pressure differential term, so that has to stay. We're going to assume that there's no frictional losses through the pump, because that is where the efficiency is already worked into play. So the friction losses already is accounted through the efficiency of the pump. So we are left with all these terms. So let's move everything over and keep this pressure term on this side. So the pressure across the pump. Quick note, when you end up plugging this value into here, notice that it's negative, so when you plug in the negative and the negative, it'll end up becoming positive. Finding the velocities, again, we were able to say that the volumetric flow rate 3 is equal to volumetric flow rate of 2, since there's no accumulation. So we can say that the velocity 3, area 3 is equal to velocity 2, area 2. And we know, or we can just individually, for each one, say both of these are equal to the volumetric flow rate, which is given. So we can say V3 is equal to volumetric flow rate over area 3. And we can say V2 is equal to that same volumetric flow rate over this new change in area. So we can say pressure 3 minus pressure 2 over rho. I'm actually going to make the alpha go to 1 because it's still turbulent. And one thing that I do want to note is that, remember here when we were initially finding this, we divided by that gravitational constant, or conversion factor, to make everything simpler, simpler-ish. We have to do that again here for this term. We don't have to do it for the work term because it's already worked in. So you can figure out all this stuff from here, I think. So pressure 3 minus pressure 2 is now equal to rho times all this stuff, negative 1 over 2 times, that's just 32.2, the GC, times volumetric flow rate over area 3. I'm actually going to pull these out. Volumetric flow rate squared times 1 over area 3 squared minus 1 over area 2 squared. And that term is subtracted from the work shaft delivered. And that should be it. There's just one more conversion step that you would have to do. So this pressure 3 minus pressure 2 term will end up giving you 1,400-ish. That's not going to be in the correct units. You need to convert to PSI. And in order to do that, you just divide this number by 144. And you end up getting that it should be, I don't know, somewhere between 44, maybe 47 PSI. Something like that. I know the English units make it a little confusing. It's a little hard to understand, but the general approach is what's important here. What's important is understanding that the mechanical energy balance can be taken around any 2 points, and it's important to understand what gets canceled out and why. So for example, these cannot get canceled out because the diameter does change from one portion of the pump to the other, so you can't cancel them out. If the diameters were the same, you'd be able to get rid of them just because they would cancel out to 0. There's also a 0 term here because we are saying that this is on a close enough of a same plane that they're able to just cancel each other out, and knowing that there's no frictional force associated with it, that it's just this work, and also knowing that you want the pressure across it, so you need that term there. Also, just know that you can apply the Bernoulli, or this mechanical energy balance equation, from one step to another. If you wanted to do point 1 to point 3, point 2 to point 4, you can do that. Okay, I hope that helped. If you have any more questions, please feel free to email me, and yeah, have a great day.